So first things first, there are four types of materials. The first one being metals, examples such as copper or aluminum. Second are polymers, examples such as polycarbonate or polypropylene. The third one would be ceramics, porcelain or stoneware are common examples. And finally, the fourth one would be composites. A natural composite would be wood, and a synthetic composite would be carbon fiber. Now, if you're interviewing for a test engineering position or a manufacturing engineering position, I think it would be pretty beneficial for you if you're well versed in some of the more essential metals that are used in the manufacturing arena, along with polymers, and had a comparatively good understanding of carbon fiber. So let's take a deeper dive into metals and polymers. So out of the ginormous number of metals available in the market, what metals would you have to study in order to do well in your interviews? Well, there are technically three metals that I recommend you study. I'll talk to you about two of them right now, and the third one could be a self-study if you choose to study it. The two metals that I'll talk to you about would be steel and aluminum. Well, steel technically is an alloy, but I think it does count in this sense. And the third one would be copper, which I'd recommend you study in your own time. Now, out of all the interviews I've done so far, I was asked about steel and aluminum roughly 80% of the time, either as a question in passing or I was asked to do an exclusive or deep dive analysis on the two metals, either differentiating between the two metals or why I would pick one over the other. I'll get to these questions in a second. And copper, I was asked about it roughly 20 to 25% of the time. So study if you choose to kill your interview. So what is the difference between steel and aluminum? It's quite an important question to understand, so this is how I would answer it. Well, steel is roughly 3 times denser than aluminum, which means that steel would be heavier than aluminum given the same volume. Secondly, steel tends to have a higher melting point than aluminum. Steel is stiffer than aluminum too. Now, in terms of aluminum, aluminum is more corrosion resistant than steel is. It also has a higher strength to weight ratio than steel. Aluminum is generally used in the automotive or aerospace sector, whereas steel is generally used in the locomotive or construction sector. These are a few differences that I would look at when comparing steel and aluminum together. And during an interview could ask you various questions. And these are some of the questions that I was asked during my interview. The most basic ones was, tell me the difference between steel and aluminum, or why would you pick steel over aluminum, or vice versa. You'd be asked a lot of application questions, and during the course of my interviews, I was asked a shit ton of application questions. An example of one of the application questions that I was asked was, let's say you were commissioned to develop the underframe of a train. How would you develop the underframe of a train? What material would you use? Is it zinc, copper, aluminum, steel? Which one would you pick and why? Another question I was asked was, let's say you had two objects that had the same volume. One was made out of steel, one was made out of aluminum. How would you know what material each of these objects were made out of? What tests would you conduct? Another question was, tell me the difference between steel and aluminum in terms of its strength and other various properties of these metals. And you'll be asked a lot of variations of these questions, and your job is to figure out how to maneuver out of these questions like an actual pro. And in order to answer these questions, there are a few concepts that you need to study to absolutely kill it. The first concept is called stress strain curves. A stress strain diagram is a graphical representation of the mechanical properties of a material. Now, what the hell does that mean? Mechanical properties of a material. That includes stuff like elastic versus plastic deformation, the ultimate tensile strength of a material, the maximum tensile strength a material can take on before experiencing failure or breakage. Fracture point is another thing you can understand from a stress strain diagram, the relationship between stress and strain itself, as it says in the name. So here's an application-based question regarding stress strain curves. Let's say you were tasked to build a component for an airplane, that avion, and your job is to figure out the right material for this component. How would you approach it? Test engineers have told you what the maximum pressure exerted onto that component would be, and you also know what the maximum surface area of that component is. So one way to figure that out is using a stress strain curve. Now, since both of these parameters given by the test engineers and the surface area, they're good starting points, using a stress strain curve, you can find out what the elastic deformation of the material you intend on using would be, what the yield point is, the point at which conversion occurs between elastic and plastic, what plastic deformation would look like, what the ultimate tensile strength would look like, what the fracture point is. And based on other parameters that you would use to kind of figure out a couple of materials, you could dial down and zero down the exact material that would work best with this application. That's how you would answer this question. Now, I guess I could talk to you more about steel and aluminum and how their stress strain curve looks like, because I'm sure in at least one of your interviews you might be asked about. So the stress strain curve for aluminum, put that down here, aluminum. Well, it's relatively straightforward. It's a 2-axis graph. On your y-axis, you have your stress, and your x-axis, you have your strain. Before we get to anything, what is stress and what is strain? is defined by this formula where stress equals to force over area, the amount of force applied over a certain area, and strain is defined as delta L over L, where delta L is a deformation of a certain rod or cylinder or whatever, and L is your original length of the cylinder. What this means is, let's say you have a certain rod or beam, and I pull it from one side. Of course, it's going to deform to a certain extent, right? It's going to elongate. This distance is your delta L, and your original distance right here, that is your L. Simple? Right. Now, the stress strain curve for aluminum, relatively straightforward. We have a linear relationship when it comes to our stress and strain at first, and then we have a point called the yield point. At this point, an elastic deformation, which we saw at this point, switches to plastic deformation, and therefore it's no longer linear and becomes a curve, hits its maximum tensile strength, and then goes down, and then fractures at this very point. Call this our fracture point, FP. This is our ultimate tensile strength. This is our yield point. Now, this point over here is called Young's modulus, very important stuff. It's the slope of this linear relationship. So since the slope, E equals to stress over strain. Now, this kind of directly tells us how stiff a material is. So the steeper the E is, the steeper the slope is, the stiffer the material is. In this case, aluminum is rather malleable and ductile because it has a lower Young's modulus, and therefore it's quite bendable in a sense. We get to steel in a second, and steel happens to be stiffer than aluminum and has a higher Young's modulus, which I'll talk to you in a second about. Now let's draw a couple of lines here. This is a point at which our elastic deformation changes to plastic. You can write this down here. This is elastic, and then this thing, everything from here on is plastic deformation, which means that it's irreversible in terms of its deformation. You also make a little demarcation here. This line over here, this stuff is called strain hardening or work hardening. It's a manufacturing technique used to deform a certain or strengthen a certain material by plastic deformation. You could plastically deform a metal or a polymer. An example of this would be copper, zinc. The alloy of these two materials, brads, is commonly deformed to make it harder. That's what strain hardening or work hardening is. And then anything till this fracture point is called necking. Necking is a process in which a material, a highly localized amount of strain is applied to a certain point on their material, and therefore it causes this curved inverse situation to a point where it just breaks. That's what necking is. So yeah, this is your stress strain curve for aluminum. It's not too complicated, it's fine. Let's move on to steel. Now, steel also has a relatively similar stress strain curve. Let's go down steel here. We have our two axes once again, our X and Y. And our Y-axis, we have what? Our stress. And our X-axis, we have our strain. Now, just like aluminum, we start off with a linear relationship, our Young's modulus. But this time it's steeper. And if you notice over here, we have not one, but two yield points. It goes one and then curves downwards. And then it makes our curved, hits our ultimate tensile strength, and then fractures at this point. Now, you might be wondering why there are two yield points. Well, that's because of the interstitial atoms present inside the microstructure of steel, which kind of makes it a two yield point type of situation in this curve. You have our ultimate tensile strength at this point, UTS. We have a fracture point, P. Similar stuff. We draw our demarcation lines here again. Similar stuff. You have our strain hardening. And we have necking that occurs right after our ultimate tensile strength. As I said, necking is a mode of tensile deformation where a high amount of strain is localized at a certain point on your beam to a point where it starts to curve inwards and then just breaks. That's what it is. Now again, our slope is called Young's modulus. That's E. And that's how it is. So we can just write down elastic deformation at this point, as mentioned previously. And then everything beyond this is plastic deformation. I think that should be it. Yeah, so this is basically how you do stress strain curves for steel and aluminum. Now, one question you definitely would be asked during an interview for, let's say, a manufacturing position is compare aluminum and steel in terms of its stress strain curves. So before we get there, I want to talk to you about Young's modulus. Once again, very important stuff. As mentioned previously, Young's modulus is defined by the letter E. The Young's modulus of steel is greater than the Young's modulus of aluminum. Now, what does this mean? This means that aluminum is less stiff in comparison to that of, let's say, steel, which means that steel is less likely to bend in comparison to aluminum. Therefore, if you break this down to a formula, we know that Young's modulus is stress over strain for steel, say, is again greater than the stress over strain for aluminum. So steel is stiffer than aluminum. Remember that, it's very important. If I had to plot both of them on the same graph, let's plot this out here. This is my stress, and this is my strain. Simple stuff. I'll use a red for steel. So again, we have our linear relationship goes up here. And as mentioned previously, we have two yield points, and then we have a big jump, and then our fracture point. This is steel, by the way. And this is our slope for Young's modulus. Now, if I had to draw out, let's say, aluminum, that would look something like this. And then we have our curve and our X point here. This is our ultimate tensile strength. This is aluminum. But again, this is not designed, this is not drawn to scale. This is more of an estimation of how our two graphs look like in relationship with each other. But that's the idea. See this? The slope over here is less steep in comparison to that of steel, and therefore it's less stiff than steel. And that's your answer. Strength to weight ratio. What the hell is this? In simple terms, it's the strength of the material over the density of the material. Density is mass over volume. But what would it matter if I said strength to weight ratio of aluminum was better than that of steel? Why would it matter to you, right? Here's a simple analogy to help you understand this better. Now, let's say a man who weighs 100 kgs walks into the gym and lifts 200 kgs. Technically, his strength to weight ratio is 200 divided by 100, giving you 2. Now, let's say 1 hour later, a person weighing 400 kgs is capable of lifting 200 kgs still. So his strength to weight ratio will be 200 over 400, giving you half. So if you compare person A and person B, person A is more efficient than person B in terms of his strength to the amount of weight that he has, or the weight that he is comprised of. That's what strength to weight ratio is. So replace person A with aluminum and person B with steel, and that's what the comparison of strength to weight ratio between aluminum and steel is. Aluminum gives you a better bang for a buck when it comes to the amount of strength that it provides for the weight. That's why planes are made out of aluminum and not steel, because the structural plane is optimized to be lightweight and strong. That's what you get when you have aluminum. But if you use steel, you get heavyweight and strong, which is a waste of gas when you think about it. Carrying the plane from one side to the other made out of unnecessary weight that comes from steel, that's not a good idea. So here's an interview question. You have aluminum, carbon fiber, and steel. How would you assess the strength to weight ratio from most effective to least effective? The answer, surprisingly, is carbon fiber is much better than aluminum and steel in terms of strength to weight ratio. It actually blows steel and aluminum right out of the water. It's extremely strong and very lightweight. So it's carbon fiber, aluminum, and then steel. So the real question is, why not build every lightweight product out of carbon fiber? Well, you can't really do that, can you? Because first of all, carbon fiber is extremely expensive. Second, it's harder to machine, because let's say you try to drill a hole into carbon fiber, and then you drill a hole, chances of cracks occurring on the side of the hole are a lot higher. And the third one would be, it doesn't work well with water since it's made out of resin and carbon fiber strands. Over time, the structural integrity of carbon fiber tends to deteriorate, so that would be a good idea too. So yeah, that would be the answer to that question. You can always get into more detail by studying some more, answer the question accordingly. Here's an interview question. Carbon fiber, aluminum, and steel, what are their applicational uses? Where would you use them? So the prosthetic sector or the sporting goods sector generally use carbon fibers simply because weight is of the utmost importance. You need something that's very lightweight and can offer the most amount of strength. Therefore, carbon fiber comes into play, and it's very effective in that sense of the way. Aluminum is generally used in the automotive or airline sector because weight is important, but not as important as let's say, a sporting good or racket would be. So yeah, planes and cars are made out of aluminum. And finally, steel is generally used in, let's say, the locomotive sector, the train sector, because a train needs to keep traction on the train tracks at all points, and slippage should not be there at all, basically, right? So you'd want a train to be made out of steel simply because it pushes all the weight down to the tracks and avoids slippage at best. Therefore, you'd use steel, carbon fiber, and aluminum accordingly. S-N curves is another graphical representation that talks about the number of cycles to failure for a certain material when an applied stress is added to it. It is used commonly in the aerospace engineering, automotive, structural, mechanical, and even product testing industries. The S-N curve for steel, how does it look? Well, on the y-axis, we have our strength. The x-axis, we have the number of cycles to failure. We start off with our ultimate tensile strength, the UTS. We have a little downward slope, and then we have a sharp plummet. And then finally, we have a straight line called the Neuralink limit. What endurance limit. Now, this is quite an important concept to understand. Why this says in the name, endurance limit is the limit that the material is capable of enduring, the stress limit, to be more precise, or the stress cyclic amplitude limit that the material is capable of withstanding before experiencing failure. At any stress level below this point, the material can experience as many number of cyclic loads on it and not experience failure. So you can keep going on for as many number of cycles to infinity, basically, and not experience failure. But anything beyond this point, the material will tend to fail at a certain stress and a certain number of cycles. So to make it a little more easy to understand, you could make a line here. This is your finite life cycle. So at some point within this framework right here, the material will fail. So there's going to be, and there's a number of cycles that the material will withstand, and after that, it just breaks. At this point, anything beyond this, it's infinite. So its lifespan, in a certain sense, is infinite. That's theoretically what it means. That's your S&M curve for steel. Nothing too bad, nothing too hard to understand. It's relatively straightforward. The S&M curve for aluminum, again, very straightforward. We have an x-axis and a y-axis. In our y-axis, we have our strength. X-axis, we have the number of cycles of failure. And unlike steel that had a couple of bounces that occurred through the course of the graph, aluminum is just a beautiful curve. It starts off here, just curves all the way down, and then fails at the end. That's the failure point. Now, the biggest difference between aluminum and steel in terms of the S&M curve is the endurance limit. Steel has an endurance limit, and aluminum does not. It fails at a certain point. Remember that. That's the biggest difference between both these curves. So yeah, let's keep that in mind, and that should be it. Polymers are plastics, a very common material used in our everyday life. Now, the way I approached studying for this plastic or polymer section was that I was quite familiar with 3D printing. I thought maybe if I studied all the plastics that were commonly used in 3D printing, that might be a good start. The first one was PLA plastic, a biopolymer, which is made out of cornstarch and sugarcane. Now, what that means is it's biocompatible and biodegradable too. So even if you breathe the fumes of PLA plastic, you won't die. It's pretty cool. The second one is ABS plastic. It's a synthetic polymer. It is obviously very hard and it's more rigid in comparison to that of PLA plastic. It's more impact resistant and it's also tougher. Now, the one con on ABS plastic, if you compare that to PLA plastic, is that since ABS plastic is tougher, it's also harder to 3D print because it has a higher melting point and it requires a little more effort to kind of 3D print the part to perfection. The third plastic is nylon. And nylon is great for high accuracy precision manufacturing. Comparing it to the other three plastics, it has the highest impact resistance, it's more flexible in comparison to the other three, has the highest tensile strength, and it's incredibly good when it comes to fatigue resistance. And finally, we have TPU and PET. TPU stands for thermoplastic polyurethane. It's a common material used in making your phone cases and many sports wearables. And we have PET, which stands for polyethylene terephthalate glycol. And in situations where transparency and water resistance is of the essence, you use PET. And finally, let's talk about two plastics that are used quite commonly in mass manufacturing applications, polypropylene and polycarbonate. Polypropylene is capable of withstanding medium-sized impacts. Now, since it's non-toxic and moisture-resistant, it's an FDA-approved material to make food containers or food packages. It's also easy to machine, and it has a comparatively lower melting point than polycarbonate. Polycarbonate is capable of heavy impact and shatter resistance, and therefore it's used in heavy-duty impact situations, such as when safety glasses or bulletproof windows. It's harder to work with since it's a tougher material in general, and it has a higher melting point in comparison to that of polypropylene. We started off by talking about the four types of materials. For metals, we spoke about aluminum and steel. We also went over concepts such as stress-strain curves, strength-to-weight ratio, and SM diagrams. For polymers, we spoke about the specific polymers used in 3D printing applications, and finally ended off by talking about polycarbonate and polypropylene.